Chemical Nomenclature, Part 5. Ionic Compounds, turning chemical formulas into names. We're going to do some practice. First, some important points. For ionic compounds, when you turn formulas into names, remember that the positive ion goes first, the negative ion goes second. Once we identify those ions, then we just name those ions. And we're going to always write the ion formulas out so that we can correctly identify the ions. That'll also help to remind us that if we have more than one possible charge, we have to use a Roman numeral. Remember that NH41+, the ammonium ion, is the only polyatomic ion that we will be using. Look out for polyatomic ions and be careful, it can be tricky. It's important that you can use a reference sheet like this ion sheet to look up polyatomic ion names and formulas, or you could use a larger reference book, or I guess you could Google it too. And again, don't forget that we use Roman numerals when the positive ion has more than one possible charge. We don't see that happening with negative ions, but we do see that happening sometimes with positive ions. So let's take a look at some examples. Here we have CaCl2. Now Ca is in this column on the periodic table. That's calcium element. It's got a 2+ charge when it forms an ion. We want to always make sure that if we find an ion on the periodic table, that we always double check and see if it has more than one possible charge up here. If it's listed up here with more than one possible charge, that means that we have to use a Roman numeral when we name that formula. Now we see that calcium ion is not listed here with any other possible charges. So that means that calcium, Ca, is always 2+. Now Cl is the negative part of that compound. So we know that Cl is here, and that's got a 1- charge. And negative ions don't ever have more than one possible charge. We're not going to see any negative ions listed up there. So Cl 1-. All right, so our ions are Cl, Ca2+, and Cl 1-. Let's just verify those are correct. And you don't have to do all this work in red. Typically, you wouldn't write that out. Once you have these down, you could probably do this stuff in red here in your head. So we'll take that 2 there and that 1 there, and hey, that's going to give us that formula, right? We typically don't write the 1 in the formula. So now we just name the ions. Calcium chloride. Remember that when we're using monatomic negative ions, we use an IDE suffix. So we don't call it chlorine, we call it chloride. And monatomic positive ions just get the element name. So Ca2+ is called the calcium ion, Cl 1- is called the chloride ion. So this compound is called calcium chloride. Let's take a look at another example. Here we have Aln. All right, Al is right here on the periodic table. That's aluminum, and aluminum can form a 3+ charge, so we'd call that the aluminum ion. It's not listed up here with any other possible charges. Always double check. And N is in the 3- column there. So we know the ions are going to be Al 3+ and N 3-. If we crisscross those, 3 and 3, initially Al3N3 reduces down because we can divide them both by the same number. 3 divided by 3 is 1, 3 divided by 3 is 1. We get Al1N1. So we just name these ions aluminum for Al3+, and N is nitrogen, so when it's N3-, we call it nitride. Again, monatomic negative ions have an IDE ending. So this is called aluminum nitride. Now, just a quick note. You might notice that nitrogen is listed up here with a bunch of positive charges. 1+, 2+, 3+, 4+, 5+. Well, compounds are always made with a positive part first, negative part second. So when we see nitrogen in the second part of the compound, we know that's got to be the negative version of nitrogen. We're not going to worry about using any of these positive charges for nitrogen when it comes in the negative part. That's something to really be clear about. Like charges repel, so we're not going to see a compound with positives and positives. It's always going to be positive with a negative. So be careful about that. If nitrogen's in the second part of the compound, we're not using any of these positive versions of nitrogen. We're using N3 minus. Let's consider a few more examples. Here we have BaCO3. All right, Ba is right here on the periodic table. That element is called barium, and that's in the 2 plus column. We'll check up here and we see that barium's not listed with any other charges up here. These are pretty much alphabetized by the symbol of the element, so you will see Ba is not here. CO3 is the negative part of the compound. Now remember that we can divide the compound up after the first element unless we see the ammonium ion. So we know barium's the positive part and CO3 must be the negative part. If we look on the ion sheet, and again these are kind of alphabetized by the first letter in the ion symbol, we'll see that CO3, well, it's listed right there, it's carbonate. Hey, be careful. CO3 2 minus is carbonate. HCO3 1 minus can either be called bicarbonate or a little bit more of a modern version of the name is hydrogen carbonate ion. So we're looking at CO3 2 minus. We don't see any H in here, right? All right, so if we use those ions, Ba2 plus and CO3 2 minus, and once you have these written out, the rest of this you could probably do in your head, right? 2 and 2 crisscross, we get Ba2 CO3 taken twice, but the 2's reduce down, so we get Ba1 CO3 taken once. We don't really need the 1's, and then we don't need the parentheses, so we just write it that way. Hey, we have the correct ions. Let's name those ions. Positive ions are just named with the element name, so Ba2 plus is called the barium ion, and CO3 2 minus, what was that again? There it is, carbonate. So you're going to want to have one of these things in your pocket all the time. All right, so let's look at another example. Here we have NH4 taken 3 times PO4. The parentheses are a pretty dead giveaway there. The NH4 is the positive part of the compound, and then this must be the negative part. So remember that NH4, that's our one polyatomic ion we're going to keep an eye out for. Remember that the ammonium ion is really only important for acid-base chemistry, or rather the hydronium ion, so we can just ignore that. So NH4 1 plus, ammonium, is the positive ion. And it turns out that PO4 3 minus is going to be our negative ion. If we look up here for some type of a PO ion, we'll see that there's a few possibilities. We have PO4, so there it is. PO4 3 minus is phosphate. So guess what? We have ammonium phosphate. And we can verify that those are the correct ions. The 1 goes there and the 3 goes there. And we'd get NH4 in parentheses with a 3 outside of it, and then PO4 in parentheses with a 1 outside of it. Now, we don't need the 1 and we don't need the parentheses around the PO4, but we can't get rid of that 3, so we need to leave the parentheses around the NH4 and leave the 3 there. So we would read this formula as NH4 taken 3 times. Again, when you say it's taken so many times, it means that that ion you just mentioned is in parentheses. PO4, NH4 taken 3 times PO4. Ammonium ion, phosphate ion, so it's ammonium phosphate. All right, let's take a look at a few more examples. Practice, practice, practice. Here we have Na2SO3. All right, so Na is right here on the periodic table. It's in the 1 plus column. Let's double check and we'll see it's not listed up here with any other possible charges. So Na is sodium, so Na1 plus is the sodium ion. And then SO3, well, that's sulfite. SO3's got a 2 minus charge. So Na1 plus SO3 2 minus look like our ions. Let's just double check. The 1 goes there and the 2 goes there, and yep, this is the formula if we don't write the parentheses in the 1. So these are the correct ions. Sodium ion, sulfite ion. The compound is sodium sulfite. It's all about finding the ions. So the more familiar you can be with where the ions are and the quicker you can find those, the easier this is. So NH4, C2H3O2. There's that NH4. We're going to divide the compound up after that. So we'll say that, right? The NH4 is the positive part, C2H3O2 is the negative part. It looks like it's a big ugly compound, but really it's just made of two parts. NH4 1+ is the ammonium ion, and that means C2H3O2, well, there it is. That's called the acetate ion. This is ammonium acetate, right? They both have a 1+ and a 1, they both have a charge of 1, right? 1+ and 1-, so 1 of each. That would give us that without writing the 1s in the parentheses. And by the way, if you wrote it this way, that wouldn't be incorrect. Typically, nobody does that. You know, writing parentheses and putting 1s there is just a little bit tedious, so we just avoid doing that. So we are going to call this ammonium acetate. The ammonium ion and the acetate ion make the ammonium acetate compound. Again, it's all about finding the ions. CuCl. Cu is in the middle part of the table. It's listed right here. We can't determine its charge based on its location. So based on experiment, the results of those experiments are written up here. Cu could be 1+ or 2+. Cl, that's got to be the negative version of it, is in the 1- column. Now be careful again. You might see that Cl is listed. There it is, a Cl with a bunch of positive charges, but we don't need Cl as a positive. We already have a positive in the compound. Positive, negative for these compounds, right? We're looking for a negative version of Cl. Always have positive ion first, negative ion second. So we're going to be using Cl 1-. This is going to be some type of a copper chloride. Cu is copper. So is it the 1+ or the 2+? Well, we can see it's the 1+. We just do a little bit of crisscrossing there. 1 and 1, right? 1 and 1 would give us Cu1Cl1. Well, that's our formula. So this is copper 1 chloride, Roman numeral 1. Hey, what if you tried to use the 2? If we put the 2 there and the 1 there, we'd get CuCl2. This compound would be made with Cu2+, so we call it copper 2 chloride. This is copper 1 chloride. Remember, the Roman numeral indicates what the charge is. Let's take a look at another example. PbCrO4. So Pb is right here on the periodic table. That's called lead. So when they sealed pipes, they used to use lead to seal pipes. And who sealed up the pipes? Plumbers. In Latin, that's called plumbum. Okay, so it looks like when it's positive, it's 4+. Now remember that the elements in this column could be 4+ or 4-. For example, when we have C4+, it's called the carbon ion. But when we have C with a 4- charge, we call it the carbide ion. So here we have Pb4+. Hey, let's double check at the top and see if it's made, if it makes any other ions. And in fact, well, it does. Somewhat unexpectedly, Pb can do a 2+ charge as well. So we have Pb2+ or 4+. Well, guess what? More than one charge like that, we have to use a Roman numeral. We either have to call this lead 2 or lead 4. And then what's CrO4? That's got to be the negative part of the compound, right? Well, here it is. CrO4 has a 2- charge. It's called chromate. So we have some type of a lead chromate. Which one is it? So Pb2+ and Pb4+ are both possibilities. CrO4 is a 2-. Let's try the 2+ first. If we crisscross 2+ and 2-, and we drop the 2 down and the 2 down, and we drop the plus and minus sign, we initially get Pb2, CrO4 2, or CrO4 taken twice. Those reduce down. 2 divided by 2 is 1. 2 divided by 2 is 1. So that becomes Pb1 CrO4 taken once. So that means we're using Pb2+, right, to get that formula. Pb2+ and CrO4 2-. So we're going to call this lead 2 chromate. Now, you'll see there's no 2 here at all in the formula. Remember that the 2 indicates the positive charge that was used. The 2 doesn't really relate directly to any number on the bottom there. I guess you could say, well, it was a 2 at one point, but then it reduced away. Again, the Roman numeral tells us what the charge is for the positive ion, not what any of the subscripts are. The subscripts are those numbers on the bottom. Just real quick, if we had tried Pb4+, 4 would have gone down there and 2 would have gone down there, and we initially would get Pb2, right? This 2 goes here. CrO4, this 4 goes here, right? So 2 and 4. But 2 and 4 can be reduced. 2 divided by 2 is 1. 4 divided by 2 is 2. This would be PbCrO4 taken twice. So this compound would be lead 4 chromate. And here we're looking at lead 2 chromate. So it can be a little bit tricky. You really have to make sure that you are writing the ions out. So here's about as tricky as it can get. Let's consider AuClO3 taken 3 times. Now Au, that's gold, that's right here. We can't determine its charge based on its location on the table, right? There are no charges written above there. But by experiment, we know that Au is 1 plus and 3 plus. So, ever since the Enlightenment, we've been writing down information that we have discovered so other people can use it. It's lucky for us. People have experimented with all these different elements to determine their possible positive charges. Notice that Au has more than one possible charge. It could be a 1 plus. Another possibility is it could be a 3 plus. So we're going to have gold Roman numeral 1 or gold Roman numeral 3 here in this compound. All right, but what's ClO? Remember that halogen oxides, fluorine, chlorine, bromine, and iodine are all halogens, follow this general pattern. And here it is for Cls. So ClO, well, there it is. It's got a 1 minus charge. It's called hypochlorite ion. So we have some type of a gold hypochlorite. If gold could be 1 plus or 3 plus, and I think it's important that you list all of the ion charges when there's more than one possible. So this will give us a visual cue when we see more than one charge that we have to use a Roman numeral. And I actually like to circle the charge that's correct to make sure that the charge represents the Roman numeral. Notice the 3 would go down here, the 1 would go there, and we'd get Au1 ClO taken 3 times. So it's not ClO3 to the 1 or to the 1 minus ion. It's not this ion. It's not the chlorate ion. It's the hypochlorite ion. If we use this, we would get a different compound. Let's consider this compound. Kind of looks like that one, doesn't it? Notice the difference in that this one, that this one has parentheses and this one has no parentheses. All right, so Au could be 1 plus or 3 plus. But now we have ClO3, 1 minus. We have chlorate. So you have to be careful when you're choosing these ions because they sometimes look really similar to each other. So if we have a 3 there and we crisscross Au1 plus and ClO3 1 minus, we get one of each, right? One of each. We don't write the ones. We don't need the parentheses. We get that formula. So this is gold 1 chlorate. Notice that the ion here is not ClO, right? It's not this ion. It was this ion. So that's pretty tricky. It's important that you write out all the ions. It's not always going to be that tricky, but it can be. So if you know how to do this, you start to build up some site recognition. And I just want to caution you that you can't really rely too much on site recognition because it doesn't always work. Instead, you should always write the ions out. Now, in practice, just like when you're reading, you typically use site recognition, and that's fine. But if you're actually being evaluated on naming, or we're going to take a look at some of the tricky ones when we do this. So when we do some of the problems on the assignment, make sure you write the ions out. All right, so you might say, hey, NaCl, that's sodium chloride, right? Sodium ion, chloride ion. Site recognition, sodium chloride. Aluminum oxide, right? Aluminum ion, oxide ion. You might say, hey, copper. Well, I know copper has more than one charge. I remember that. Could be copper 1 or 2. Well, there's a 1 down here, right? It's 1 and 1, so we'll call that copper 1 chloride. And that, in fact, would be correct. You might look at this one and say, well, yeah, copper could be 1 plus or 2 plus. Since there's a 2 down here, we must have crisscrossed a 2. That's copper 2 chloride. You know what? That would be correct, too. So you get away with site recognition, with a little bit of drill and practice, that's fine, but you run into tricky ones like this. You might be tempted to look at PtO2 and say, hey, that's platinum 2 oxide, but that's incorrect. This is really platinum 4 oxide. That's because when you crisscross 4 plus with O2 minus, the 4 goes there and the 2 goes there, and 2 and 4 reduce to 1 and 2. So this is platinum 4 oxide. This is platinum 2 oxide. So don't just rely on site recognition. Again, every chemical bottle that we use, if you go in the stockroom, you'll see it has both the formula and the name on the chemical, because guess what? These are different chemicals, and they do behave differently. All right, so if you know what we're doing here, you should be able to, taking these ionic compounds, turn the ionic compound formulas into names. And when you do this, make sure that you show 2 steps. Write the ions out and write the names of those ions to get the compound name. Make sure you show both steps, 2 steps for each one of these. CaBr2, Fe2CO3 taken 3 times, Na2SO4, ZNS, Kf. Remember, K is potassium. NH4OH. Now remember that. It's kind of an oddball here, but we have a couple exceptions mixed in with these ites and the eights. Cyanide is CN1 minus, and hydroxide is OH1 minus. So we've got a hydroxide here. All right, NH4 taken twice, C2O4, CRO, AgCl, and Mg3PO4 taken twice. Now before we wrap this up, and I have to admit I'm a little bit reluctant to mention this, but I think you might find that you're in a lab sometime and that you grab a chemical bottle and it has one of these names on it, so we should be aware of it. I'm reluctant to mention this because I'm hoping that sooner or later this stops being used. But sometimes you will see that traditional Latin names are still in use for some positive ions. We see this more specifically for copper, iron, and tin. These are really old metals. They've been around since ancient times, since the Roman Empire was still around, and Romans spoke Latin. So they called copper cuprum, right? Cu, cuprum. They called iron ferrum, Fe for ferrum. And they called tin stannum, Sn for stannum. So you might grab a chemical bottle still today and see that it's named with cuprous or cupric, ferrous or ferric, stannous or stannic. Now, in general, the way this system works is that we use us for the smaller of the possible charges, ic for the larger charge. So for copper, the smaller one is 1 plus, the bigger one is 2 plus. So copper 1 could be called cuprous, and copper 2 could be called cupric. Iron, the smaller one is 2 plus, bigger one is 3 plus. So iron 2 plus is ferrous, iron 3 plus is ferric. Tin 2 plus is stannous, tin 4 plus is stannic. So for example, CuCl, it's made of Cu1 plus and Cl1 minus, is copper 1 chloride, or you might see it named as cuprous chloride. And CuCl2, that's made of Cu2 plus and Cl1 minus, that's copper 2 chloride. You might see that named as cupric chloride. So that's just something to be aware of, really, if you see it on a chemical bottle. But I think it's best practice to not use these Latin names and instead stick with Roman numeral names.